Standard integrals. The integral of the basic power of x has been covered in a previous video. Now we're going to look at the trigonometric, exponential and logarithmic functions. Starting with the derivatives, then we can have a look at these derivatives and work back to integrals. Take note of the plus c in every case because these are indefinite integrals. Useful to have them in your memory, to know them already. Well, if you know the derivatives, then the integrals follow automatically. Here's some exercise to kick off with, to try yourself. In number 1, multiply out the bracket first, and we have two standard integrals, giving you tan x plus sec x plus c. In number 2, we have standard integrals, e to the x and 1 over x, so it goes straight to the integral. In number 3, let's divide that into 1 over sine x times cos over sine x, because those are two recognizable trigonometric functions, being cosec and cot. And there is another standard integral now, negative cosec x plus c. In number 4, let's distribute the denominator each of the terms in the numerator. And it's a straightforward integration now of two terms, where 1 over x has the standard integral of ln x. Number 5, let's square out the bracket. Remember, we're squaring a binomial. Square the first, multiply the two together and double, square the last. Now recognize that these two here, we have our Pythagorean identity, sine squared plus cos squared, which is equal to 1. And in the middle here is a double angle formula. Remember that 2 sine theta cos theta is sine 2 theta. Therefore 2 sine x over 2 cos x over 2 becomes sine twice of x over 2, which is sine x. So we have 1 plus sine x. And those are standard, so it's just x minus cos of x plus c. Now we're differentiating by inspection at this stage, and we'll continue a little bit further. What this really means is we're not using any of the recognized techniques of integration, just going straight from the original to the answer. Now if we have a look at this one, we know that e to the x gives you back e to the x. So let's try that first of all. So e to the 2x gives us back e to the 2x plus c. Question mark, let's test it. How do we test an integral to see if it's correct? By differentiating it. So let's differentiate this, and we end up with that, because e to the 2x is e to the 2x times derivative of the inside, which is 2. Now if we compare, that and that should be exactly the same, and they are not. What's happened is, because of that chain rule, which has given us that extra 2 which cropped up, we need to allow for that in the integral at this stage. So we're going to put it times a half, which means we'll have times a half in the derivative, and half times 2, the 2 is gone. Now they compare favorably, so therefore we know that our integral has to be e to the 2x multiplied by half plus c. Now here's a useful technique for working out this sort of constant or this sort of coefficient. It can be quite mind-boggling to work it out sometimes if you have some more complex numbers along the way. So when we have something like this, we know that e to the 2/3 x is going to come back at us. So I'm going to write that as k times e to the 2/3 x plus c. We're not sure of the coefficient, but now what I'm going to do is differentiate this and compare to what we're integrating. So the derivative of this is that there, and I'm going to compare that to what we're integrating because they should be the same. Well, we have e to the 2/3 x in both cases, meaning that 2/3 k must equal to 3, giving us k is 9/2. So there's our integral, 9/2 instead of k, and we have our integral. Another case of this technique, that is the integral of 3x plus 1 to the half. Now I know that when we integrate something, we add 1 on, so therefore we're going to go to 1.5. So let's hope that if we have k times 3x plus 1 to the 1.5, it may come back as very near that. So let's try it. Differentiate it. We end up with that, which we'll simplify to there. Now, if you have a look, the 9/2k, we have the same bracket exactly, so it's just 9/2k where there it's 1. So we can put 9/2k equal to 1, which means k is 2/9. So we put 2/9 in there, and there is our integral. Another case with trigonometry now. The integral of sine is negative cos. The integral of sine is negative cos. Therefore, I think that there's a negative cos involved. So I'm going to put negative cos 3x minus pi, and I'll put a k there, which goes to there. Next step, differentiate and compare my result to what we're integrating. There we are. That should be exactly the same as that, which gives us that 3k is equal to minus 3k is equal to 2. K is minus 2/3. Minus 2/3 instead of the k there or there, and there is our integral. In this next one, a bit more complex because the x is outside and inside two different places, so you need to be a bit observant in this case. There are signs of a chain rule, because if you have a look at derivative of the denominator, you get 2x minus 4, just twice x minus 2. The top line is 3 times x minus 2. So it looks as if the top line is related to the derivative of the denominator. So therefore I think that this is ln of x squared minus 4x plus 1. Integral of 1 over x is ln x, so integral of 1 over something is ln. There is this there, but I think this is the chain rule linked to the chain rule derivative of the inside. So let's differentiate that. So it's 1 over x squared minus 4x plus 1 with a k times derivative of the inside is 2x minus 4, which gives us that. So we have what in effect is 2k into x minus 2 and 3 into x minus 2. Let's equate them to one another, which gives us that k is 3/2. So therefore 3/2 can come back here and it'll make this derivative of our integral exactly the same as what we're integrating. There are some exercises to try. In number 1, sec squared 5x, well, we have sec squared, there we are, it's tan, so related to tan 5x, so I'll make it k tan 5x, differentiate, and compare that to what we were differentiating there, so 5k is the same as 1. So therefore, our k must be 1/5, and there is our integral. Next one, number 2, well, that's got to be ln x. K ln x. Differentiate it, we get k over x as opposed to 3 over x. Therefore, k must be 3, so therefore 3 ln x plus. The next one, yes, this is e to the 3x, so therefore k times e to the 3x. Differentiate it, so 3k is equal to 1, so k is 1/3. Sec 2x tan 2x. Yes, sec tan. So this must be sec of 2x with a k. Differentiating, we get 2k sec 2x tan 2x as opposed to 3 sec 2x tan 2x. So therefore this 2k must be the same as the 3, making k 3 over 2. 5x minus 2 all to the half, which means 5x minus 2 to the 1 1/2, or 3 over 2. Differentiate, we get 3 over 2k, 5x minus 2 to the 3 over 2, times 5 being derivative of the inside, which means in effect 15k over 2 must equal 1. Which means k is 2/15. So there we are. There's our integral. Number 6, we have the same case of if we differentiate that, we get 2x minus 2, which is twice x minus 1. So this looks like the derivative of the inside, so it's a chain rule. So we'll say, well, this must come from x minus 1, x minus 2, x squared minus 2x to the minus a half. So therefore, x squared minus 2x all to the half. If we differentiate that, we get half k to the minus half. That looks right. Differentiate it. There it is there. Compare it to that there. Well, we have the x minus 1. We have the x squared minus 2x square rooted in the bottom, so therefore 3k is the same as 1. So k is 1/3. So there is our integral. But further with trigonometric integration. Integration is quite a bit more complex than differentiation. When we see this sort of thing, we need to say, well, where have we seen that before? There we are. We've seen it before in this sort of expansion. Sine 2x plus 5x or sine 2x minus 5x would give us our sine 2x cos 5x patterns. There they are there. Now I want sine 2x cos 5x. These. I don't want those. So this is adding, that's subtracting. Why don't we add these two together? These will go, and I'll end up with this plus this equals that, 2 sine 2x 5x. Which means now I can just divide by 2, and I'll end up with sine 2x cos 5x is equal to half into sine 7x, 2x plus 5x, minus sine 3x, well that's sine of minus 3x, which becomes minus sine 3x. There it is there. So now, this we can integrate. Integral of that is the same as integral of that. The half can go to the outside of the integration sign. Now these are two terms, we can integrate them separately. That becomes minus cos x over 7. That becomes minus cos x over 3. Changing that to a plus. And we have the half outside. So the over 7 becomes over 14. Over 3 becomes over 6. Plus c. And there are two other formulae as well to give you your sine, sine, and cos, cos. So we have our sine, cos. Sine, sine must come from the cos expansions. Cos, cos must come from the cos expansions. So there are the three. Those are usually on a formula sheet. But if not, you can work them out. If you see a sine, cos, you can say, well, that's the sine expansion. So let's take my two sine expansions. Sine A plus B, sine A minus B. And how do I combine them to get what we have? Now, another example, integral of sine squared x dx. Now, that's a problem. I can't say that's k sine q dx because I'll end up with getting a cos out of the inside function in chain rule. So we rewrite this. I remind you that cos 2x is 1 minus 2 sine squared x. Now this double angle formula is very useful. And many people make the error of forgetting about this. Now we can solve that for sine squared. There we are. Sine squared x equals half into 1 minus cos 2x. So if we're integrating sine squared, we're going to integrate half into 1 minus cos 2x. The half can come to the outside because it's just a constant factor, and we're going to integrate each of those. So that becomes x with a half. This there becomes minus sine 2x times a half, which times that half gives you a quarter. And the cos expansion, same way. Cos, we'll end up with cos 2x equal to 2 cos squared x minus 1. And it'll give us that formula there. Some practice. Sine cos. So we have a look and say, well, which one has a sine cos? There we are. So it's 4x 7x. So the sine cos, I'm going to have 4x 7x, 4x 7x. So we end up with sine 11x plus sine negative 3x becomes negative sine 3x. That becomes negative cos 11x over 11 times a half. That becomes negative with that positive cos 3x over 3 times a half. Plus your c. Cos, well, there's the cos expansion. So therefore I'm going to have cos of x minus 3x plus cos of x plus 3x. That's cos of negative 2x, and remember that cos drops the negative. When we say cos of negative 2x, we think of negative 2x as a little bit. Which quadrant? Fourth, where cos is positive. So therefore we'll have cos 2x plus cos 4x. This will give you sin x over 2 times a half. This will give you cos 2x over 2. Sin 2x over 2, I'm getting there in the end. Sin 2x over 2 times a half will give you sin 2x over 4. This here will give you sin 4x over 4 times a half gives over 8. Number 3, we're going to separate it into two integrals. I've written that as our expansion there. It's twice cos squared x, so therefore we lose the half. We have 1 plus cos 2x. Now we can integrate each of those separately. Remember the half there again, as we got the extra over 2 there, over 4 there, over 11, over 3, because when we differentiate this, we have a 2 coming out of chain rule, so we need that to counteract. When differentiating this, we have a 3 coming out of the chain rule, which means we need the third to counteract because there's no number there. Well, there's a 1. Number 4, same sort of situation. We apply the rule. So it's 3 over 2, 3 times, and then half that, which means I'll have 3 over 2 integrated 3 over 2x. That there, when we integrate it, will become negative sine 2x over 2 times 3 over 2 gives you your 3/4 sine 2x. And sine x cos x, well, we can apply the sine cos, or we could use the fact that actually we see that's virtually the double angle formula. That's half of sine 2x. Sine 2x is 2 sine x cos x. That's 2 sine x cos x with the 2 gone. And that becomes negative quarter cos 2x plus c. If you applied sine cos, that formula, you'd end up with the same thing, because there you'd end up with your half sine 2x plus sine 0. So we'll end up with that. It just went shorter because we're observant. Here's some more integrations originating from chain rule. What I suggest you do is try and finding the derivative of each of these, or you could try integrating each of these separately, but try otherwise, because these are the answers, differentiating each of these to see if you get the original. And that'll give you some insight into the differentiation by inspection of the results of chain rule, because that's a result of chain rule. If we differentiate that, we use chain rule.